Designing a counter is very important. As I mentioned previously, we can design our own circuitry as we wish to, and we will just see a few examples and we'll try and understand how to build the same. Okay. For your syllabus point of view, okay, we have building of synchronous counters. Okay, synchronous counters is there for your syllabus point of view. But here, what I have done is I have asynchronous counters as well. Okay, you can just refer this for your information. Okay, for your understanding, and I will just brief you up on these asynchronous type, and then quickly we will move on to what is there for our syllabus. Right. So asynchronous, as you all know, this should have a clock, okay, which is the output of the previous state. Okay, so this is one way of easily telling as to what kind of um, uh, is it clocked or is it synchronous or asynchronous type of counter. Okay, so here it is negative edge triggered. How do I know it's negative edge triggered? Because of the symbol here. Okay, and j k is equal to 1, we use toggling effect. Okay, j and k, when it is 1, we use toggling effect. Fine, these are our waveforms, normally how we used to see at negative clock cycle. Okay, right. So one more important thing that you can know here is for 3 bits or 2 bits asynchronous counters. Okay, for 2-bit asynchronous counters, I need 2 flip-flops. For 3 bits, 3. For 4 bits, 4. For 5 bits, 5 flip-flops. So the number of bits is equal to the number of flip-flops. Okay. So that is one thing that you can remember. And the other thing that you have to know is if it's a 2-bit counter, okay, so the combination is going to be 0, 0, 0, 1, 1, 0, 1, 1, right? And the maximum count is going to be 2 raised to n minus 1. So here 2 raised to 2 minus 1 is equal to 3, right? So which means it is going from 0 to 3, 0, 1, 2, 3. So that is what it means. And n, the power that we give n, is actually the number of bits. Understanding, students? We all following what I'm trying to say? Yes?
Yes, sir.
Okay. So here, if we have to put that in the form of states, okay, this is what state diagram. So 0, 1, 2, 3. So these are the states, right? Suppose I take a 3-bit counter, okay, and if I have to draw the state diagram, okay, so this is how it's going to be. You can see that I've used the color coding here, okay, which is the one in black, okay, and the one in red, okay. So it is going in two directions. So if you follow the red one, okay, then it is up counting, okay. If you follow the black one, okay, then it is down counting. So which means it is going from one from triple one to final triple zero. Okay, so there are two ways in which this counting is happening. So which means this is a up down counter. So down counter is in anti-clockwise and up counter is in clockwise. So two types, right? So designing now, I will show you as to how this designing can be done. Okay, just give me a moment. You will be able to understand all of these. Okay, once we actually look into the design part of it. Okay, now this is important. Okay, these points are important here, where you have modulus of the counter and counting up to a particular value. So as I told you, n is nothing but your number of bits. Okay, and if I say mod number is equal to 2 raised to n, okay, then 2 raised to 2 is equal to 4, 2 raised to 3 is equal to 8. Okay, So the first thing that we have to do is find out how many bits, and based on that we can know how many states. Okay, so if it's 2 raised to 2, then 4, then maximum count will be 2 raised to n minus 1. Okay, so it will be from 0 to 3. So 2-bit up or down counter is mod 4, then 3 bits is mod 8, 4-bit is mod 16. It is just like 2 raised to whatever is the number of bits. Okay, so that is called your mod count. Fine. So here if I say the number of states are 6, okay, mod 6, then the maximum count is going to be till 5, because it is 0 to 5. Okay, 1 0 1. Right, this is not that important. Uh, right, these are some of the extra points that I have written here, okay, just for your understanding. Negative edge triggered Q is the clock and then up counts. Positive edge triggered Q bar is the clock and it up counts. If it is negative edge triggered, then if Q bar is the clock, then it down counts. If it's positive edge triggered and Q is the clock, then it is down counting. Okay. Yeah. Now this is our topic of interest. Okay. From here, I want you all to concentrate properly, and we will try and design the synchronous counters, right? So the step one is decide the number of flip-flops. So how will I decide the number of flip-flops, students? As we have seen previously, how do I decide how many number of flip-flops? Based on
So number of bits.
exactly. So how many bits? So many flip-flops. Okay. Next, the excitation table of the flip-flop. Now, how do we get the excitation table? If you can recollect, how do we get the excitation table?
So from the characteristic equation.
Yes, from the characteristic equation or from the characteristic table, we actually analyze, and from that we get the uh, excitation table. Okay, right. So excitation table of the flip-flop is needed, and how many number of flip-flops is needed, that is to be analyzed. Then state diagram we can draw, and then circuit excitation table we have to create, obtain simplified equations using Kmap, draw the logic diagram. So if we follow these 5 steps, okay, it's going to be easy for us. According to me, the main thing that is needed is the excitation table. Okay, the excitation table is the main thing needed here, and to make things more simpler, you can also use the state diagram. Okay, so if you can follow steps 2 and steps 3, okay, so that is going to be much simpler, wherein you can uh, design any counter. Okay, so let us take uh, the first one as an example. The problem is design a 2-bit synchronous up counter. Okay, so when I say synchronous, the clocks are given separately. Okay, and 2 bits. It's hinting us that I need to use 2 flip-flops, 2 bits, 2 flip-flops. So JK flip-flop. So in fact, they can ask anything here. Okay, so here in the question they have not specified that you have to use a JK flip-flop, but we will be using a JK flip-flop just because we have an advantage, right? We have an advantage of the 1-1 state, right? But in SR, 1-1 becomes invalid, right? So we do not want that state. Instead, we can use this. So as we all know, this is our excitation table of JK flip-flop. Okay, so I am using JK flip-flop to design this counter. So in the question, they can even specifically say use T flip-flop to design, use D flip-flop to design. Okay, but here it's a generic question. It says design 2-bit synchronous up counter. So design a counter which is synchronous and which is which is synchronous and which does not have the clocks, right, connected to each other, right? Okay. So the next one, what we have to do, we have to decide that with the number of states, right? So in order to decide the number of states, I need to draw the state diagram, right? So since we know that it's a 2-bit 00011011 2-bit, so which means 2 raised to n is equal to 4. Okay, so I will have states from 0 to 3. Okay, so 00011011. So for 00, I will name it as state 0. For 01, I will name it as state 1, state 2, state 3. Okay, so similarly S0, S1, S2, S3. So I will give this kind of state diagram. Are you all clear till this concept? Till this concept, is it clear?
Yes,
What all
sir.
we did so far? Yeah, okay. So we are checking the question, we are seeing how many bits, and based on that, if a specific flip-flop is asked, we will use that. If not, we will generally go with JK flip-flop. Then I will draw the state diagram. So once I have the state diagram, now this is very important. Okay, your circuit excitation table. So what you should do here is you should have 0, 0, 0, 1, 1, 0, 1, 1. First, try to understand the concept of this circuit excitation table. Now you have two Q1s and two Q2s. Okay, Q1 and Q1 star, Q2 and Q2 star. So which means this is our next state. Star is representing our next state. Okay, these two are representing our next state. Now, how do I get this next state? Okay, just concentrate. Now here, you should even refer to your state diagram. Okay, yeah. So just refer to your state diagram. Now, as usual, these will be used based on our normal binary form. Okay, which is 0, 0, 0, 1, 1, 0, 1, 1. This is our normal binary form. So Q1, Q2 is done. Now, after 0, 0, what state is coming? Okay, so after 0, 0 here, if you see, what state am I going into? S0 is going to which state? After the clock pulse. Be loud.
S1.
S1, right? So S1 means 0, 1. So I have to write after 0, 0, it is going to 0, 1. Okay. In the next one, after 0, 1, it is going to 1, 0. After 1, 0, it is going to 1, 1. After 1, 1, it is going back to, after 1, 1, it is going back to 0, 0. Right? So this is how you fill Q1, Q2, Q1 bar, Q1 star and Q2 star. Any doubt still here, students? Till here, any doubts?
Sir, how did the Q1 star and Q2 star come, sir?
Next state, I am filling it. I am filling it. This table first we will fill. Okay, 0, 0, 0, 1, 1, 0, 1, 1. First we will fill. Understood? After that, I will take it step by step. After 0, 0, I will fill 0, 1. Because see the state
So, sir,
diagram
those
here.
are the next states which we are considering.
Ah, yes. So that is
Oh,
why
okay,
we
sir.
have a star here. Star means what? Next state. Outputs next state.
Yes, sir.
Okay, so see the state diagram here. Based on the state diagram, I am getting this Q1 star and Q2 star. Okay, so after 0, 0 is 0, 1. See, after 0, 0, I have 0, 1, right? So 0, 0 corresponds to 0, 1. So till this concept, I think we are clear, right? Okay, so now let us move to the next concept. Now we have filled the first column. and the second column. Now we are interested in the third and the fourth. Can someone tell me how did we get this J1, K1 and J2, K2? Now, okay. Now we have to compare two things here, Q1 and Q1 star. Okay. So this will be as good as uh, your excitation table. Okay. So consider only these two, Q1 and Q1 star. Consider only these two. So Q1 star corresponds to J1 K1. Okay. So how do we get that? This is based on your excitation table. 0 0 is 0, don't care. Next 0 1 is 1, don't care. 1 1 is don't care, 0. Next 1 0 is don't care, 1. Is that clear, students? Is it clear? Students, I want you to respond. If not, it becomes a one-way communication. Surya has responded.
Yes, sir.
Okay, fine. Thank you. Next, what we will do is in the same manner, okay, we will consider Q2. Okay, take only Q2 and Q2 star. So using these two, I will get my J2 K2. So here I have 0 0, sorry, 0 1. So for 0 1, it is 1, don't care. Okay, for 1 0, it is don't care, 1. For 0 1 is 1, don't care. For 1 0, it is don't care, 1. So this is how I obtain my circuit excitation table. Any doubts here, students? Any doubts how we have got this circuit excitation table? Can I proceed? Okay. Now, once we have this truth table, okay, it's easy, or rather to say excitation table. Okay, the next step is to develop our Kmap. Okay, to develop the Kmap. So go back to our steps, and you can see we have decided the number of flip-flops. Excitation table is done. We have selected JK. We have drawn the state diagram, and we have also developed the circuit excitation table. Now we are in step 4. Step 4 is nothing but your simplified equation. So how will I get simplified if I have a Kmap? How will I get a Kmap? I have to fill values inside the Kmap, right? Okay, so how do I fill based on my excitation table? So separately, I will be using for J1, K1, okay, J2 and K2. Okay, separately I will be using. So how will I fill this? Okay, so I will be using my Q1, Q2, these values, normal values. Okay, so 0, 1, 2, 3, but I will be filling the values of J1. So at 0, I'm filling this. Okay, at the 0 cell. Okay, then at the first cell, I'm filling 1. Then here 2. This is for 3. So which means separately I have done for J1. Any doubts here, students? Any doubts here? Can I proceed? Okay, thank you, Surya. So similarly, what I will do, I will draw a map for K1, I will draw a map for J2, I will take a map for K2. Once we have the K map, we have to go with grouping, right? So this is nothing but our 0, 1. Since you all know now, I have not written all this 0, 1. Okay. So these two will get cancelled, 0, 1. Okay, so only Q2, high Q2 will be there. So J1 is equal to Q2. Similarly, K1 is equal to Q2, J2 is equal to 1, K2 is equal to also 1. Okay, how did I get 1? Because I have a quad here. Okay, I have a quad, maximum number of ones. So once I have these, what is my next step? My next step is to just draw the diagram. How do I draw the diagram? I take JK flip-flop, okay, the first JK flip-flop, then I take the second JK flip-flop, I put the clock, as usual, I connect the clock, okay, and J1, K1, Q1, Q1 bar, Q2, Q2 bar. Now connections are needed, only the connections. J1 is connected to Q2, so I take the J1 here, okay, I take J1 here and I connect it to Q2. Okay. Next, K1 is also connected to Q2. So which means I can connect J and K together, short it, and directly connect to Q2. So J1 connection is done, K1 connection is done. J2 and K2, I have to give 1. So what I can do, J and K together, I will short them. Okay, together I will short them, connect them, and connect directly them to logic 1. So in this case, okay, we have designed our counter using JK flip-flop. So as usual, we will be getting Q1 output here and Q2 output here. Any doubts, students? Is it clear?
Yes, sir.
Yeah, we are clear with the concept, right? Okay. So we will now see few more examples, okay, wherein you will be able to understand. Okay, right. 3-bit up-down synchronous counter. Okay, so what I'm going to do now is I want not only up counter, I want up and down, both I want. So in that case, what we are going to do? So this is a very interesting case, okay, where I take 3 bits, okay, and then I take another 3 bits. Now, can someone tell me which flip-flop we have used here? Have we used JK flip-flop? Or have you used D flip-flop?
T flip-flop.
T flip-flop.
Yes, T flip-flop we have used here. Okay. So the question is generic. Okay, design a 3-bit up-down synchronous counter. So here you can use T, D, JK, anything. So since I have already discussed a problem with JK, okay, I thought I will discuss one with a different flip-flop, T flip-flop, right? So we just want an up-down counter, something which goes in ascending way and something which goes in descending way. Okay, right. So what I will do here is I will have a control input just like a switch. When I give 0, then it should up count. When I give 1, then it should down count. Okay. So bifurcations, what I will do is I will have this should be A actually. Okay. This should be A, QA, QB, QC. Yeah. So as usual, I will go with 000 till 111. Okay. And then here also from 000 to 111. So this table, I think you have understood as to how we have got this column. Just a minute. Yeah. Okay. So present state is nothing but, we are going from 000 to 111, and then again 000 to 111. So actually, what I am trying to do here is I am taking 4 bits. Okay, taking 4 bits. So 4 zeros till 4 ones. Okay, so that is my count. So if you can see here, the normal binary count starts. Okay, from all zeros to all ones. Okay, so in this one, what I do, the first bit itself, only the first bit I will bifurcate and I will tell this is my control input. Okay, because I have all zeros in the first half and then I have all ones in the next half. So I will differentiate and I will tell when it is 0, I will make it up count, and when it is 1, I will make it down count. So how do I do it when I fill my next state? So how do I fill my next state now? From 0, I will go to 1. So is that up count or down count? If I'm going from 0 to 1,
Up count.
yes, it's an up count. So similarly, I will take from 1 to 2, okay, and similarly from 4 to 5, okay, I'll just fill this. And ultimately, once I reach the highest number, 111, I will go back to 0. So I am writing this table. So this is where I decide as to which function is employed or how I want my circuit to function. Okay, so this star that you see here are the next states. QC, QB, QA. These are all next states. So next I want it to down count. Okay, so what I will do, if it is a 0, 0, I will take 111. So normally for up counting, I used to take 1, but here I'm doing the reverse. So instead of 0, instead of going 1, it will go high. Okay, and then when it is 1, okay, then it will go 0. So what you can do here is you can draw a state table. Okay, so once you draw a state table, it will be easy for you to understand. Okay, so let me just show you that. So this table, I think you all understood how we wrote, right? Any doubts in this? How we got this table, this column, next state column? Any doubts here?
So the first half it
Hello?
will increase by 1, and in the second half it will decrease by 1, sir.
Yes, yes, that's all. That's all. Just descending.
Hello.
It keeps descending. That is right. We are going in a descending fashion. Okay. Were you able to hear?
Yes, sir.
Okay. So to make things more simple, what you can do is you can also refer to your state diagram here. Okay, so just see this. It will make things more simpler. Okay, so 0, 1, 2, 3, 4, 5, 6, 7. Okay, and then back to 0. So if I go in my clockwise, then it is going to be my up count. If I go in my anti-clockwise, then it is going to be my down count. So up count I will use for m is equal to 0. Okay, so this up count I will use for m is equal to 0, and down count I will use when m is equal to 1. M is equal to 1. Okay, right. So you can just see across. Let us see 0, 1, 0. So we are down counting. So 0, 1, 0. So where is our 0, 1, 0? 0, 1, 0. So which means I should go in down count. So which means I should be seeing at 0, 0, 1. Okay. So am I writing that 0, 0, 1 here? Yes. Any doubts? Now, is it clear, students?
Yes, sir.
Okay. So now for your
Yes,
understanding,
sir.
yeah, for your understanding, we will even see 111. So 111 down count means I should get 110. Okay, this 110, right? Down count. So am I getting that 110 here? Yeah, 110 is there, right? Okay. So now it is just the same. Okay, where we take the excitation table of whose excitation table should I take here? Should I take the excitation table of JK, T, D, SR? Whose? I should take the excitation table of T flip-flop, right? And similarly, I should go on comparing QC with QC. Okay, consider only these two columns and then you will get TC. Consider QB and QB star. Okay, QB and QB star, and I will get TB. Similarly, consider your QC and QC, QA and QA star. So I will get TA. So this is how I get my values. So what is my next step once I have the values in my table? Tell me. What do we do
Kmap
next?
simplify.
Yes, Kmap, and we simplify, get the equations and put them in the form of our equation. So TA, I can see here all are 1, right? All are 1. So I can just say TA is equal to 1. Then TB, I get the equation, okay, in this fashion. And TC, I get the equation in this fashion. Okay, I have not done any highlighting here. Grouping, okay, you can see I have done slight grouping in the pencil. Okay, 1 1 and 1 1. So I get two equations, two sub equations here. So I have TA, TB, TC. Once I have these equations, it is easy for me to just put them across. So TA, directly I connect to 1. Okay, TB, what is TB? TB is nothing but your M XORed with QA. Okay, so M I take M, and that is XORed with QA. Okay, is XORed with QA. And what is my TC? My TC is this equation. Okay, so ultimately I will use my logical gates here, okay, which is M bar QB QA. So M bar means I will take the output from the inverter. So I take M bar, okay, and then QB QA, QB QA. So QA and QB I multiply, use an AND gate. I use OR gate, okay, to give this sum, and the other one is taken from here. TC is given my input, right? So any doubts here, students, as to how we have implemented this? Are we clear with the concepts? Yes?
Yes, sir.
Okay, fine. Thank you. Now we will design a synchronous counter. Okay, all of you take down this problem. I want you to start solving this. Design a synchronous mod 6 counter using JK flip-flops. So I have told that it should go from 0, 1, 2, 3, 4, 5. After 5, I want it to be 0. So this is my question. Only till here is my question. Implement a mod 6 synchronous counter according to the counting sequence. Counting sequence is this, going from 0 to 0. I've given a random value here. Okay, a random value. Okay, so implement it according to this table. Have you all taken a snapshot of this? Please take a snapshot and start working with the problem.